Welcome everyone. In this lesson, we're going to be investigating the second derivative. And specifically, we're going to see how we can use that second derivative to help us locate the intervals of concavity for a function, for the graph of our function. So finding those intervals where it's concave up, the intervals where it's concave down. We're also going to see how we can use the second derivative to help us locate those inflection points. So specifically where the concavity actually changes. And then, and we'll probably get to this in class, but we'll also see how we can use this second derivative to help us classify our critical numbers. So we can use this to help us determine if we have a local max or a local min. All right, so let's start with our intervals of concavity. And the main result we're going to use is something we've talked a little bit about before, and that's this idea that if we have an interval, so some interval from a to b, if the second derivative is positive on that interval, then the graph of the original function is concave up on that same interval. And if the second derivative is negative, well then the graph of the original function is concave down on the interval. So second derivative positive means the function is concave up. Second derivative negative means the function's concave down. Okay, so we've seen that before. And so what this is really telling us is that we're interested in the sign of f double prime. So we really want to know, when is it positive, when is it negative? And so to help us locate those, we need to know, well, when does it actually change sign? And that can happen only when the second derivative is 0. And so we're really going to be interested in first locating where the second derivative is 0, because that's where the second derivative can actually change from being, say, positive to negative. So these are the possible locations where f double prime can actually switch signs, can change signs. And so these are going to be important. So we're going to give them a name. We're going to call these places the possible inflection numbers of function f. So any x value, x equal to c, where the second derivative, if we plug c in, if the second derivative is equal to 0, that's going to be what we call a possible inflection number. And so how we're actually going to find these intervals of concavity, the first step is, well, we're going to need our second derivative. So we need to actually calculate f double prime. So that's going to be the first thing we do. Get the second derivative. Once we have that, then we're going to set the second derivative equal to 0 and solve for x. Because really what we're looking for are these possible inflection numbers. So we want to find these possible inflection numbers here. Okay. And then once we set the second derivative equal to 0, we solve it for x. Then ultimately what we're interested in is the sign of f double prime. So we're going to do a sign chart for f double prime, for our second derivative. And so if you're kind of looking at this, this is the exact same procedure that we used for the intervals of increase-decrease. The only difference is now we're using the second derivative versus the first derivative. So this is basically it's the same procedure that we've used before. That we use for increase-decrease. The only difference is for intervals of concavity, now we're using the second derivative, but it's the same steps. Get the second derivative, set the second derivative equal to 0, solve that equation for x, and then do your sign chart. So let's see how this works. So let's look at example 1. And for this example, we're going to find the intervals of concavity for this function x cubed minus 3x squared plus 5. So our first step here is we got to get the second derivative. So that means we're going to calculate our first derivative, which in this case is, what is it? Derivative of the first term is 3x squared. Derivative of that second term is 6x, and then we subtract. And then the last term there is, well, it's just a constant all by itself, so it differentiates to 0. So this is our first derivative. Now, to get our second derivative, we're just going to go one more time. And that's going to give us f double prime. So if we differentiate that first term, we get 6x. And if we differentiate that last term, we get 6. And then we're subtracting. So there's our second derivative. Now, not absolutely necessary, but it can be helpful. Once you have your second derivative, try to factor it out. And in this case, 6 factors. So I might factor that out just to help make the numbers a little bit smaller. So I get 6 times x minus 1. And then, once we have that all nice and calculated and maybe factored, we're going to take our second derivative. We're going to set it equal to 0. And then we're going to solve that equation for x. So I'm going to take that factored version, the 6 times x minus 1, and I'm going to set that equal to 0. And when I do this, the variable term, the variable factor here, that's going to give me a solution for x. So I can take that variable factor, just kind of set that equal to 0, and then if I solve, I get x equal to 1. And so this x equal to 1, this is my possible inflection number. Essentially, this is a possible location for an inflection point. That's what we're going to see later on. It's not necessarily an inflection point, but it's a possible location. If our graph is going to have an inflection point, it's going to happen here. But we don't necessarily know that we do actually have one. All right, but if we keep going, next we're going to do our sign chart for f double prime. All right, so we're going to draw our x-axis. There it is. We're going to plot all of our possible inflection numbers. So in this case, just the x equals 1, and we'll throw it right there in the middle. And this splits up the x-axis into 2 intervals. So everything less than 1 and then everything greater than 1. So we have the interval from minus infinity to 1, and then the interval from 1 to infinity. And let's just use open intervals here. So I'm just using parentheses around everything. And then we're going to figure out ultimately the sign of f double prime and see what that tells us about function f. Now, to help us fill in our sign chart, the function's not too complicated here, but let's use each of these individual factors just to help us make the numbers a little bit smaller. Again, not absolutely necessary, but anything to make the numbers a little bit smaller is usually helpful. So I'm going to write down each of the factors of f double prime. So 6 and then x minus 1. So I got to include everything there. And then we're just going to go for each interval, figure out if each of those pieces, each of those factors, is it positive or negative. So for this, I can use test numbers. So maybe for this first interval, I could use 0 because 0 is less than 1. And while we're at it, the first factor here is just a constant, positive 6. So that's going to be positive on both of these intervals. The variable one, that can change. So for t equals 0, let me plug that in. I get 0 minus 1. It's negative. So ultimately what I have here is I have a positive number times a negative number. So that's going to make my second derivative negative. And when my second derivative is negative, that means the original function is concave down on that interval. Now if I go to the next interval, the interval from 1 to infinity, I could pick a test number, so maybe something like 2. You know, really anything bigger than 1 would work, but I keep it easy. Again, we know 6 is positive, so I have that there. And then I could take this test number, plug it into the variable factor. I get 2 minus 1, which is positive. So ultimately what I have here is 2 positive terms. I have a positive number times another positive number, which is going to make my second derivative positive on that first interval, or on that next interval. And so when my second derivative is positive, that means my graph is concave up. And so to kind of summarize here, my function f is concave up on the interval from 1 to infinity, and then f is concave down on the interval from minus infinity to 1. All right, so let's investigate this possible inflection number. Let's see a little bit about what this means. And so we say that we have an inflection number for our function. It's going to be a number x equals c that's actually in the domain of our function, such that f double prime is equal to 0. And f double prime actually switches signs there. So in order for it to be an inflection point or an inflection number, we actually need, this is kind of the key thing here, for it to be not just a possible inflection number, but to, full-blown inflection number, we need the second derivative to be 0 there. But more importantly, we need our second derivative to switch signs there. And that's kind of the key thing here. So really what we're doing is on our sign chart, we're looking for a sign change on the sign chart for f prime. So we'll have our sign chart. So just look for a sign change at your possible inflection numbers. And if there is one, well then it's actually an inflection number. So if we wanted to find the inflection points, so how do we actually determine the inflection points? Well, steps 1 through 3 are going to be find the intervals of concavity, essentially. So get the second derivative, figure out where the second derivative is 0, and then do your sign chart. So steps 1 through 3, same as those finding the intervals of concavity, those steps that we used. And then once you have your sign chart for f double prime, then it's just look for a sign change. At those possible inflection numbers. And this should be step 4. Skipped a step. Yeah, steps 1 through 3, same as finding the intervals of concavity. So get the second derivative, figure out where the second derivative is 0, and then do your sign chart for f double prime. Step 4 is you're going to look at your sign chart and figure out where you actually have a sign change at any of those possible inflection numbers that you found. And then depending on how the question's worded, there might be a step 5 where you might have to find the y coordinate then also for your inflection point. Depending on how the question's worded, of course. And the way you do this is you just take your inflection number and you plug it back into the original function. So you got to make sure you go back to the original function, not the second derivative. So you want to plug it into that original function f, and that'll give you your y coordinate. All right, so let's try this out. Let's go back to that first function we looked at in example 1, and we have our sign chart all filled in. So let's go through this process where we actually find the inflection points for this function. So normally we would go through, and if we kind of go back up to example 1, it would all be the same steps. So if we were going to do this problem all over again, it would be the same steps. It would be find the second derivative. Bang, we did. Then it would be set the second derivative equal to 0 and solve that for x. Yeah, we got it. X equals 1. That's our possible inflection number. And then step 3, do your sign chart for f double prime. And here we go. We have it. And so the last thing we're doing in order to find the inflection points is we want to look at all these places that we identified and see if f double prime has a sign change there, or see if our function has a change in concavity there. So if let's kind of write down our sign chart again. And so what we found in that first example is that we have these two intervals, minus infinity to 1, 1 to infinity. We found a possible inflection number right there at x equals 1. And then what we found is that f double prime was negative and then positive, which really meant that our original function was concave down and then concave up. And so what we're seeing here is there's kind of two things going on. There's actually a sign change happening right there at x equals 1. We're going from negative on one side to positive on the other side. So you can think of this a few ways. There's a change in sign for f double prime. So that's one way to think of it. The other thing you can think of is an inflection point is just where do we have a change in concavity? And we see that we have a change in concavity happening right here at x equals 1. On one side, we're concave down. On the other side, we're concave up. So we actually have a change in concavity happening. And that's precisely what it means to have an inflection point. So we have a change in concavity for the original function f. And so what this means is step 4, x equals 1, not only is it a possible inflection number, but it's actually an inflection number. We do have an inflection point here. So this means we do have an inflection point at x equals 1, because we do have that change happening, either a sign change or a change in concavity, however you want to think of it. So we do have an inflection point at x equals 1. And let's actually get the coordinates of our point here. So the last thing is we want to get the y coordinate. So let's figure out our y coordinate. And to do this, this is where we're going to plug the x value that we found back into the original function. So as we're doing this, we have a few different functions floating around. So you gotta, it kind of gets tricky. You gotta keep track of which function you have to use. So we're going to use the original function to get our y coordinate. So the y coordinate in this case is going to be f of 1. So we're just plugging our inflection point into the original function. And what was our original function? Well, here it is, x cubed minus 3x squared plus 5. So when I plug 1 into that, I get 1 cubed minus 3 times 1 squared plus 5, which is 1 minus 3 plus 5. And what is that? That is positive 3. So the y-coordinate for my inflection point is 3. So putting that all together, my actual inflection point is 1, 3. So if I were to graph this out, this would be the point that I plot, where specifically on the graph, that's the exact point where we actually change concavity. We go from concave down on one side to concave up on the other side. All right, so we're going to stop there. But in class, what we're gonna do a little more practice. So we're gonna try this again with another function. And actually, while we're at it, we'll also look at the first derivative again. Just review that, find the intervals of increase, decrease, locate any extreme points, and then we'll see how we can put all this together, all this information about the intervals of increase, decrease, the intervals of concave up, concave down, to actually produce a pretty good representative graph of, or sketch of, what f would look like. Not going to be precise, but it's going to give us a good idea of all the different behavior that's happening for our function f. So we'll see you then. Bye-bye.